Ladies and gentlemen, welcome in. It is Friday, September 23rd. I'm recording this in the afternoon. This morning in lecture, I talked about an example problem that I was going to record and do for you. So we are going to do that now. This comes from the Micromechanical slide deck notes. So I think it's slide 13. I have it here on my OneNote pad. So I'm going to transfer over now and we will do it. Okay, so we can see that I have the problem statement copied here and away we go. A unidirectional carbon epoxy composite has the following constituent properties. Modulus in the two direction of the fibers, 14.8 GPa. Modulus of the matrix, 3.45 GPa. Poisson's ratio of the matrix of 0.36. And volume fraction of the fibers of 0.65. We want to determine the transverse modulus, E2, of the composite using two different approaches. We have the mechanics of materials approach, and we have help and psi with C equal 1 or Xi equal 1, however you want to say it. Then, if the actual threshold or the actual value of the transverse modulus is 8.02 GPa, what is the error associated with either of these two methods? Okay, so let's go ahead and get into this. First of all, we can just go ahead and go with our mechanics of materials method. And so when it comes to the mechanics of materials method, we have two choices. So let's go MOM, mechanics of materials method. And we have two possible choices for the mechanics of materials method. We have the parallel model and the series model, also sometimes called the rule of mixtures and inverse rule of mixtures. So in this case, for E2, it's more common to use the inverse rule of mixtures. So our formulation for this particular portion of the problem, I'll say E2, and we'll give it an MOM at the top, mechanics of materials. This is going to be calculated according to our inverse rule of mixtures or our series model, which here is the volume fraction of the fibers over the modulus of the fibers in the two direction, plus volume fraction of the matrix over modulus of the matrix. All of this inverted to the -1. One thing that is important to note in this problem is that we do have the volume fraction of the fibers given in the problem, 0.65, but we do not have the volume fraction of the matrix, capital VM. Don't get confused here. This is the Poisson's ratio of the matrix, which is 0.36. Poisson's ratio has nothing to do with the volume fraction, right? We're looking for a volume of the fraction of the matrix, which is 1 minus the volume fraction of the fibers, which in this case is 0.35. Okay, so we'll be using that in our formulation. So let's get on with it. So in our calculation, oh, my pen got small. I'm gonna make this line a little bit wider. Let's see if I can change the width of this. All right, just making my pen a little bit larger. That's still not large enough. Okay. So according to the mechanics of materials method, let's put the numbers in. Volume fraction of the fibers here, this is 0.65. The modulus of the fibers in the two direction given 14.8 GPa. We're going to add to that volume fraction of the matrix, which is 1 minus 0.65 or 0.35. This is normalized by the modulus of the matrix, which is 3.45 GPa. All your GPAs look like that, right? All this to the -1. You can work this down, punch this into your calculator. You'll find that according to the mechanics of materials method, which here we're using the inverse rule of mixtures, according to this method, we're going to find an elastic modulus in the two direction of the composite of 6.88 GPa. All right, so this is the first part of our answer, calculating the modulus of this composite in the two direction according to the mechanics of materials method. So remember, when it comes to the mechanics of materials approach, we have inverse rule of mixtures or rule of mixtures. And when it comes to E2, the better choice is inverse rule of mixtures. Remember, this is good, inverse rule of mixtures. Also good for inverse rule of mixtures is G12. It's not great, but is okay. If we were asked to calculate, let's say, the modulus in the one direction or Poisson's ratio in the 1,2, then we'd probably want to go with the traditional rule of mixtures instead of the inverse rule of mixtures. Okay. Now let's move on with it. The next step of the problem is calculating the help and psi approach with psi equal to 1. So here they're giving us the value of psi. Typically, if you're going to calculate E2 using the help and psi approach, you'd go with a value of psi equal to 2. But we're told in the problem to use psi equal 1, so that's what we're going to do. So let's go ahead and do that. Now we're going to calculate the elastic modulus in the two direction according to the Halp and Psi equation. And we remember our Halp and Psi equation is here what's going to be the elastic modulus of the matrix, 1 plus here our psi, eta VF, all over 1 minus eta VF. So I already told in this problem the value of psi here. So we can just write straight away if we'd like. I don't know why it makes my pen so tiny. So we can go ahead and write straight away that our value of psi is equal to 1 for this problem, so that's nice. But we're still left with one unknown here, which is our value of eta. So if we remember from class, eta is another one of these weird terms that pops up in the Halp and Psi equation. It is generally here going to be property of the fiber over property of the matrix. So here it's going to be E of the fiber in the two direction over E matrix minus 1 divided by similar property of the fiber over property of the matrix plus our xi variable. So we can calculate all of these things. We have all of these. Modulus of the fiber in the two direction. This was given as 14.8 GPa. I'm going to leave off the GPa now just for simplicity's sake. This normalized by the modulus of the matrix, 3.45 GPa, all this minus 1. That entire numerator is normalized by a similar looking denominator, 14.8 over 3.45. Here now plus xi, which in this case is 1. You do this calculation, you're going to come up with an eta value, which is 0.621. Now, one thing I didn't mention in class that I feel like I probably should mention here is that the value of eta should always range between 0 and 1. Never will you have an eta outside of that range. So if you have an eta that falls outside of the range of 0 to 1, you messed up. So if this value looks like 1 point something, better go check your work. Okay, so now we're ready. We have everything, our eta value, our psi value. So we have everything else in this equation up here as well. So let's go ahead, calculate the elastic modulus in two direction according to Halp and Psi. This will be the elastic modulus of the matrix, 3.45 GPa, multiplied by 1 plus xi, which is 1, eta, which is 0.621, and volume fraction here, given in the problem, 0.65. All of this gets normalized by 1 minus eta VF. Here, eta again is 0.621, and volume fraction is 0.65. Do the hokey pokey, calculate yourself around, and you're going to find an elastic modulus in the two direction according to Halp and Psi, 8.12 GPa. All right, not quite done. We have one last portion of the problem to do, and that is if the actual value of the transverse modulus is 8.02 GPa, what is the error associated with each of the two methods? So we're going to have to calculate error twice now, one for the mechanics of materials method, one for the Halp and Psi method. And the general equation is property that is estimated minus property that is known divided by property that is known times 100. So let's first start with the mechanics of materials method, the error associated with that. So I'm going to label that here as little e associated with the mechanics of materials method. So here, this is our estimated property. So the absolute value, our estimated property here is 6.88 GPa. We're going to subtract off the known quantity here, which is 8.02. Take the absolute value of that. This will end up being a negative number in the numerator before we take the absolute value, and normalize by the known value, 8.02 GPa. You work this, typically error is represented in percent, so we'll multiply by 100 to get to a percent. This will be 14.2% error associated with the mechanics of materials method. We can do similar calculations for the error associated with the Halp and Psi calculation. Halp and Psi, we calculated the elastic modulus, again, as a reminder up here, of 8.12 GPa. So here we go, 8.12 GPa minus our known value, just given in the problem, 8.02 GPA. Here normalized now by the known value, again, 8.02 GPA. And here we'll have a significantly less error associated with this. We're going to get 1.3% error according to the help and psi calculation. So you can see in this one particular example, help and psi is much more precise. Typically that is true. Remember, the inverse rule of mixtures for calculating E2 neglects stress concentration. So help and psi will generally be more accurate. That's it for this example. You have homework problems that are very similar to this, so I'll leave it here. Any questions, feel free to email me or come to my office hours every day at 8 o'clock. See you later.